Welcome to AP Calculus, Chapter 6, the definite integral. We're going to be estimating some sums, typically areas, what are referred to as areas under the curve. We have done a little bit of this, we've practiced. I'm going to be working under the assumption that you have some exposure to LRAM, left-hand rectangular approximation method, RRAM, our right-hand rectangular approximation method, and midpoint rectangular approximation method. Also, hopefully by this point you have a RAM program in your calculator. If not, that's something that you want to be taking a look at. Okay, this notation means the area under a curve, and under a curve implies to the x-axis of some function. So here's my function defined from a to b, is written this way. And that area, if I have infinity intervals, like I'm going to subdivide that into all sorts of tiny little rectangles, as many rectangles as I can fit in here, and I just add up all the area of the rectangles, whether it's left-handed, right-handed, or midpoint. If I could get infinity of those, I would get the true area. So we just keep dividing it down. Now clearly, if I only had, let's say, here's A to B, if I was just going to try to do this with, say, 3 rectangles, RRAM, I should have a different color to illustrate. Let's say I was just going to divide that into 3 RRAM. Then we have all sorts of possibility of errors, but if I put more and more and more subdivisions in here, the rectangles get closer and closer and closer together, and their sum of their areas closely approximates, or by the time I have infinity rectangles, the theory would be we have the exact area of what's inside there, of what's underneath the curve. Okay, so we'll also call this the area under the curve from A to B. Again, area under the curve implies to the x-axis. Okay, so a particle starts at x equals 0 and moves along the x-axis with velocity. So we got a velocity curve here. Velocity t squared plus 1 for time t greater than or equals 0. Where's the particle at t equals 4? Let's make some sense out of this. I'm going to graph the velocity curve. So here's v of t, or y equals v of t. I'm going to go 1, 2, 3, 4. And this is t squared plus 1. So by the time I get to 4, I'm up at 17. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And this is 1, 2, 3, 4. Our velocity, now, they don't give me units here, but a velocity might be something like feet per second. Now, if that's feet per second, then this would be seconds. Okay, we're going to come back and talk about that. It's not feet per second, it's not seconds, but it could be miles per hour, hours. Anyway, it's a velocity versus a time unit. So let's go ahead and get a picture of this. At time equals 0, we are at 1. And at time equals 1, we are at 2. And at time equals 2, we are up at 5. And at time equals 3, that might be a little overshot. At time equals 3, we're up at 10. And at time equals 4, we're all the way up at our 17. And we know that this is a parabola. In fact, we know it's a parabola with vertex right here at 0. So this gives us a pretty good look at our curve, and what we're looking for is the area between the x-axis from here to here. Okay, approximate the area under using 4 rectangles of equal width. So I'm going to build rectangles by partitioning into 4 equal widths here. And I don't think I'm quite drawn accurately, but we're going to say these are all equal widths, and they're widths of 1. And we want to use midpoints, so that is like a flashing neon light that says, hey, we're using MRAM. And what MRAM does is we go halfway through our partitions to 1/2 here. I'm going to put that in here. We'll come back to that. 3 halves, 5 halves, 7 halves. We're going to go to 1/2. We're going to go up to the midpoint. We're going to build left, and we're going to build right, and there's our rectangle. At 3/2, I'm going to go up to the where the midpoint hits the axis. Build to the left and the right, covering my interval with a height at 3/2. Go to 5/2. Where do we hit? Up in here. Build the rectangle left. Build the rectangle right. At 7/2. I don't know why I have 7/2 too, just 7/2. Might be somewhere right in here. Build left. Build right. And the suggestion would be that if I find the area of each of these green rectangles, add those together, that would be the close to the area underneath the curve of that. And we see, obviously, there's some faults. I don't expect this is going to be an exact answer, but I do have a little overage here, and that doesn't exactly fit there, I don't think. I have a little underage here, not including that in my rectangles, but we realize it's going to be somewhat reasonable, and midpoints, MRAM's oftentimes a better choice than LRAM, RRAM. Kind of depends on what the curve looks like, but MRAM, when in doubt, MRAM is probably going to give us a better approximation. So let's talk about the area of these guys. The area of this first rectangle. So here's my area approximation. Is width 1 times height. Well, how high is it? It's the height of our function at 1/2, or it is v of 1/2. I'm going to put 1/2 in here. Plus triangle 2, well, it has a width of 1 times the height at 3/2, so v of 3/2, plus the third one has a width of 1 times the height at 5/2, v of 5/2, plus 1 times v of 7/2. And by the time I get to there, there's my first, second, third, and fourth rectangles. Now, oftentimes the width isn't 1. But since it's 1, we know we can drop it, but here's typically how I would set this one up. I would say, let's just factor the width out, and now we just need all of our heights. Well, let's start finding our heights, and I think we may be able to do those in our head. Put in 1/2, and I get 1/4 plus 4/4, 5/4. Put in 3/2, and I get 9/4 plus 4/4, 13/4. Put in 5/2, and I get 25/4 plus 4/4, 29/4. And put in 7/2, and I get 49/4 plus 4/4, 53/4. So let's see, that is 1 times, I'm going to go backwards here, that would be 82, 92, 95, 100 on 4. That was convenient. 25, so we are at 25. What unit would we be in here? Is we would be in, that is just plain old feet. Now you're saying it's an area, it must be feet squared. No, our units, because along the way I'm multiplying seconds times feet per second, it's just feet. Approximate the area under the curve. The area under the curve is 25 square units. What would it mean as far as where are we? We are 25 feet down the road. The 25 square units really is just a plain old, in this case, feet unit. So the area is 25 square units. We're moving along the x-axis. We've moved a positive 25. Where is the particle? Don't say it. Never say it. The particle is at 25 on the x-axis. Okay. All right. So working with velocity curve there, just a little bit different. Typically we've been working with position curves and then talking about velocity. Okay, example 2. Region R refers to the area enclosed by this guy. And the x-axis 0 is less than or equal to x is less than or equal to 2. Sketch the region. Partition it into 4 sub-intervals. And we're going to use LRAM. And we're going to compute LRAM without the sum of without using our calculator. So from 0 to 2, when I put in 0, I get 0. When I put in 2, I get 4 minus 4, 0. When I put in 1, I get 2 minus 1, 1. Oh, this is an upside down parabola. and the vertex is at 1, 1. So I'm not going to skimp and have a small graph here. I'm going from 0 to 2. I know I have a point here, point there. You could T-chart this. You could figure out where the vertex is, but I've got all of that information. This is an upside-down parabola. And we're supposed to use LRAM with 4 subintervals. So I am supposed to take that and divide that. Let's see, this would be 1, this would be 1/2, 3/2, and 2. I'm supposed to divide that into these and build rectangles LRAM, which means in my first rectangle, I go up the left side till I hit the curve. Well, I'm already at it. This is a rectangle with no height in theory. Then I go up the left side until I hit and build my next rectangle. Then I go up the left side until I hit this, build my next rectangle. Up the left side till I hit the curve, build my next rectangle. So our approximate area is my widths are 1/2, and then I want, if I call this f of x, my widths, I want my widths at, I want my height at the first one. That would be f of 0 plus, this one has a height at 1/2, f of 1/2 plus f of 1 plus f of 3/2. I don't want to talk about f of 2. This is left hand. I'd be outside of my region. So just a little bit of quick calculation. Notice the half would distribute in, and then each of those would be my rectangles, the area of my 4 rectangles. So I just start, if it's a constant width, I just start by factoring out the 1/2. So f of 0 is clearly 0 plus f of 1/2. F of 1/2, I'm just going to do my scratch work up here, would be 1 minus 1/4, 3/4, plus f of 1 is 2 minus 1, 1, plus f of 3/2, that would be 3 minus 9/4, or 12/4 minus 9/4, 3/4. So my area is approximately, let's see, 1/2 times, that would be 6/4, or 3/2 plus 2/2, 5/2 for 5/4. Do we have units? We don't have units, but we're approximating the area, so that would be square units. Okay. Now, depending on what this was a graph of, the final answer might be miles. If this was velocity in miles per hour, and this was hours, when I multiply these things together, that width hours by that height miles per hour, the hours cancel, and I just get miles. So that would be like how far we've traveled if this was our velocity over 2 hours. This was a graph of our velocity. And again, just an approximation, and maybe not a great one. We might want to partition this a whole lot more than just 4 partitions. Okay, use a calculator program to find RAM. I'm going to leave that to you if you do not have that calculator program. But again, what would we do? We'd enter y1 as if we were going to graph 2x minus x squared. We would run our RAM program. It would ask us for intervals. We'd enter 10 intervals, left bound 0, right bound 2. And we would get approximations based on 10 intervals. Wouldn't want to have to do that by hand. It's going to take a while. Certainly wouldn't want to have to do 500 by hand. And what we end up finding out as we move through this program, we get down to 500, these are going to get closer and closer together, and they're actually going to start to appear like maybe we know what the answer to this really is. Maybe we know the exact answer to that, but I'm going to leave that to you. You have your calculator program, but I guess I will tell you that by the time we get to 500, we're going to be dealing with something very close to 1.333 in each of these. And they'll be off by some decimal point beyond that. So we start saying this is when we become scientists. Maybe the area under this curve from 0 to 2 is 4/3. But again, I'll leave that to you. Again, number 4, very similar. Use RAM to estimate. What are we going to do? We're going to go ahead and enter this as our Y1 in our RAM program that we have written. We're going to enter interval. Well, we can enter however many intervals we want, but hopefully what we learned up here is probably the more the better. Now, your calculator will have some limitations. If you try to enter 1,000,000 rectangles, I don't think it's going to work on you. So you might have to play around with that a little bit. And so we would enter this as Y1. We would enter maybe 500 intervals, and left bound, right bound, and our calculator is going to give that to us. Again, that should be something that you guys do on your own. I will just put it here so you can test it. At 500 intervals, I got the area is approximately 0.884. Okay, so we start to look for some convergence between our LRAM, MRAM, and RRAM. And if we've got good convergence, we're probably in pretty good shape, and we do converge at 0.884-ish. Okay. And we got this distance traveled upstream. You were walking along the bank of a tidal river, watching the incoming tide carry a bottle upstream. You record the velocity of the flow every 5 minutes for an hour, with the results shown in the table below. How far upstream does the bottle travel during that hour? Find LRAM, find RRAM estimates using 12 subintervals of length 5. Now, first thing in this, I believe this is a misprint. This should be 25. If not, it changes this problem a little bit. The next thing I look at this, our time is in minutes, but every 5 minutes for an hour, our velocity is in meters per second. And basically when we're finding areas, we're multiplying height, I'm multiplying minutes by, or excuse me, this is my height of the graph, the velocity. I'd be multiplying meters per second times the x-axis value, which is minutes. Now I got conflicting values here. So I either need to convert this into meters per minute, or this into seconds. So I'm going to convert this into seconds. This would be 300, 600, 900, etc., down to 3600. So I might want to use those values. Now, I'd like you to try to think about this for a little bit. Maybe you're going to pause this and see if you can come up with this without seeing the graph. Maybe you can just picture the graph in your head and see if you can figure out what's going on. What would the difference be how we find LRAM and RRAM? This is not going to be one, since we don't have a defined function. We can't put it in our calculator. 12 subintervals. Notice we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 endpoints, but if I treat this as a rectangle from 55 to 60, 50 to 55, we would have 12 of those. Okay. So this would be a good time to pause, see if you can come up with an approach to this without just drawing out a graph. But then I'm going to draw out the graph. So pause it. And welcome back. Hey, you didn't pause it. I'm just kidding. Let's take a look. So I'm going to graph time from 0 to 3600, or at least some of that. So I'm not going to do all of it. You're going to get the picture here. So we've got 300, 600, 900. I'm going to put a break in the graph here, and we're going to jump to, what's 55 times 60? I'm going to cheat. I think it's 3,300, isn't it? 55 times 60, 3,300. Oh yeah, I could have done that because I could have come back from 3,600. And I'm going to break to here. So my values go as high as 2 along the way. So at 0, we are at 1. At 300, we're at 1.2. Approximating here. At 600, we're at 1.7. At 900, we're at 2. And then breaking the graph, at 3,300, we're at 1.2. And at 60, we're at 0. Okay. So our LRAM would involve this. LRAM would involve partitioning this. Here's our partitions. It would involve going to the left side of this first partition. It would involve this. So here is LRAM. LRAM would be, all the intervals are 300 wide. My first height is 1. My second height is that 1.2. Plus dot, dot, dot. I'm going to go 1 plus 1.2 plus 1.7 plus 2. How far am I going to go? At 3,300, this is our 1.2. I build that rectangle, LRAM. Do I now go to here and build another rectangle? No, I've reached the end. That's my 12. I'm actually using for LRAM those values. Whereas for RRAM, my widths are 300, but RRAM, I would actually build my rectangle from the right side. And this one would actually be down here. So my RRAM, my first rectangle would actually be 1.2. My second one would be 1.7, and my last one I actually would use that 0 value. So the RRAM values would include that last step, but not the beginning of the, or the end of the last increment, but not the beginning of the first, versus the LRAM, which includes the left-hand value, not the very final right-hand value. So hope that makes sense to you. We got some challenges that we're going to need to be taking a look at here. I do plan on getting some of the homework problems put up. Again, if you don't have that LRAM, RRAM program, there's lots of places you can find it, but if you would go to, if you would Google, I'm certain if you would Google Hart's Math RAM program, I wouldn't be surprised if you could find it. But you can come in. I'd be happy to go through that with you. It's all over the internet, all sorts of different sources where you can enter that in your calculator and find those. It'll do a lot of heavy lifting work for you. Doesn't mean we aren't still going to have to at times go through the process as we did in this lesson. So there's a look at your assignment, and good luck and ask questions.